Good afternoon, ladies and gentlemen. Woo! Section 5.2, Power Functions and Polynomials. I don't know about you, I'm excited. We're starting to get into stuff that may not have been discussed very much in other classes, finally. As it turns out, this is some big material today, and so got a lot of pieces. But each of these pieces, if you note how they fit together, will be really easy to handle. If not, it's going to take some extra practice, so make sure to take a look at some of our notes, and the textbook is here to help out. So let's get started on section 5.2. Your homework assignment for today, page 372/390, 1 through 45 odds. Keeping it simple. Okay, first thing to point out today, the first big category we're going to talk about is going to be power functions. And let's start with a nice definition. What is a power function? Or a power function is anything of the form f of x is equal to kx to the n power. Where in this case, k is a constant, so it's a number, like 3, like pi, like -14, but it's a number. And n is an integer that is positive. So, it doesn't always have to be this case. We'll talk more about negative power functions later on. But really, it's just they have to be a power. So what makes this thing a power function? Well, one big detail. There is nothing being added or subtracted. That's what makes a power function. Okay, it's just a number times x to a power, which means that some examples of power functions. Ones you may have seen, x squared. That's an example. What about something like just 4x, like a line? That's an example of a power function because it has a constant, 4, x, and a power of x, which is the hidden 1. You could also have things like the square root of x. This can be a power function. And it turns out when we look at our list here in a moment, this is actually one of the common ones. And so integer isn't really appropriate here. It can be any number. Okay, next, you could also have things like, this is a weird one though, x cubed minus 6x cubed. Yes, I know it has subtraction in it, and I said before you can't have subtraction, but this can actually be simplified. So one of the things you may need to do is check to see if they can simplify. It is possible something is a power function, it's just not simplified. And so it's always good to look at it in that form. Similarly, you guys don't like x squared times 3x to the 4th. Like this isn't in that form, but if you simplified it, it would be. And so these are all considered to be power functions. And in fact, here's a list of some of the most common ones. So, some of the most common ones. F of x is equal to 1. This is called the constant function. F of x equals x. This is referred to as the identity. F of x equals x squared. This is the quadratic function. X cubed is the cubic function. You can even talk about x to the 4th as the quartic, but for now we're going to go ahead and go to the other common ones, which is like 1 over x, which is the reciprocal. You could have 1 over x squared, which is the reciprocal squared function. And then you can have the fun ones, where you have things like the square root of x, which is of course the square root function. And of course the cube root of x, which is, the cube root function. these are all considered to be really common power functions. And so any one of these is considered a power function. And if you multiplied it by a number, these would also be power functions. And these don't have to just be x's. It's important to note too. These could be something like, classic formula from geometry, 4/3 pi r cubed. This is a volume of a sphere formula from geometry. 4/3 is a number, pi is a number, so you have a number times a variable to the third power. That's just a power function, because it's a constant times a variable to a power. That's a power function. So all 6 of these are examples of less classical power functions, but here are the standard list of power functions. Now, why on earth do we talk about power functions? Well, as it turns out, all power functions follow very specific rules. And the rules depend upon what kind of function it is. And the first set of these rules is referred to as end behavior. If you know the end behavior of a function, you can determine exactly what kind of function it is and how it will act as we go towards negative infinity and positive infinity. So we define end behavior as what happens to the left, or as we prefer to write it, as x goes to negative infinity, and to the right, or as x goes to positive infinity. So if you're thinking about what a graph of this thing looks like, what's happening as we move all the way to the left? What's happening as we move all the way to the right? And it turns out it depends upon 2 factors. And these factors are listed in this table. This table is a great piece to have for your notes. An important thing to note about this table is the middle part of this does not matter. This inner piece is not the important part. It's these outer pieces that really, really matter. And so, let's copy our table. It's a good one to have, and really helps to solidify all the components we need for today. Okay. What happens if our k is bigger than 0? So remember, k comes from that constant part. So in this example, k is positive. This example, k is positive. And this example, k is actually negative, because when you simplify it, it's in a different form. K would be positive, k would be positive. So what happens if k is positive? Well, there's 2 big cases that matter a lot, and these have to do whenever you have even or odd powers. So notice this excludes several examples, like the reciprocal function is not included in this list. The reciprocal squared function is not included. The square root function and the cube root function, we're not talking about their end behaviors because they have special cases. What we're talking about is these more general functions, like x, x squared, x cubed, and then higher numbers too, like x to the 17th power. It turns out, because the number is the 17, you can make specific predictions about what that function is going to do as we move to the left and as we move to the right. So let's talk about each of these when x is positive. Okay, when you have an even power and your x or your k is positive, what's going to happen is they're going to go in the same direction upwards. Notice how I'm leaving this middle part blank? That's because I don't want to forget that in the middle here, some weird stuff can happen. Like, it could be, one side dips lower than the other. It could be that there's some weird, squiggle in the middle. We don't sure, but if you have an even power, the farther left you go, the more up it's going to go. The farther right you go, the more up it's going to go. This is referred to again as end behavior. What's happening as we move towards negative infinity and positive infinity on the x-axis. As we move to negative infinity, the left-hand side goes up and the right-hand side goes up. If it's odd, we have a slightly different version. If it's odd, the left-hand side goes down and the right-hand side goes up. Now, the way your textbook describes this is it states the following. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. In other words, it doesn't matter if you move to the right or to the left, it's going to go to infinity. As long as k is positive and the power is even, this will happen. On the other hand, the following happens on the other side. As x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. This is always the case if you have an odd function. So the constant function will do this. The cubic function will do this. The identity function will do this. These have odd powers, so they will always have this behavior. Okay, what happens if your k is less than 0? So in other words, what happens if k is negative? Well, slightly different story. Okay, if your k is negative, it's going to essentially flip this thing upside down. For both of them. So in other words, as x goes to negative infinity, f of x is going to go to negative infinity. As x goes to positive infinity, f of x is going to go to negative infinity. So notice negative infinity just means going down, and since f of x, it means that f of x, that y value is negative infinity, going downwards. So as we go farther to the left, the graph goes down. That's how you interpret this statement. As x, that's left to right, goes to the left, f of x, that's your y, goes down. So as we go left, the function goes down. As we go right, the function goes down still. And so even functions can have two possibilities, but notice how similar they are. Either both ends go up or both ends go down. That is because it's an even function. With an odd function, you have the opposite effect. But again, there's similarities everywhere. As x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to negative infinity. Again, let's interpret. As we move to the left, our graph moves down. Up. Sorry, I'm crazy today. As we move to the left, we go up. As we move to the right, we go down. And so using these descriptors, you can do two things. You can predict what the function is by looking at the graph, or you can predict the graph by looking at the function. So an example of this. If you look down one, it says, describe the behavior of x to the 8th power. To answer this question, it's a simple search and find of which of these four boxes we're talking about. And so let's answer these questions. Is this thing even or odd? Is k bigger than 0 or is k less than 0? Because depending on which of these things we answer, it's going to tell us what our end behavior is going to be. So in this case, we have an even power, and our k is bigger than 0. Because again, the number out front is a 1, and 1 is bigger than 0. So this tells me my end behavior is going to be from this first box up here, meaning as k goes to infinity, f of x goes to infinity, and as x approaches negative infinity, then f of x approaches infinity. This is our definition of the end behavior. And some people like to use the shorthand, up, up, where you describe what happens to left first. So left up and right up. So if you look at these examples, k greater than 0 and even would mean up, up, left up, right up. K less than 0 would be left down, right down. So up, up, down, down. Whereas odd would be down, up, and then up, down. You always describe it left to right, like as if you're reading a word. You read left to right. So if the function ever asks, what is the end behavior? What we're looking for is this. And notice how we answer it. We answer it by identifying is it even or odd, Is it greater than 0 or is it less than 0 for the coefficient? And sometimes it's not always as easy to answer as it seems. So for example, if I gave a different one for the text, let's say negative 2x times x to the third, this is actually a power function. I'd have to simplify it first so that I can actually get to a function that is useful. I'm going to change this to x squared. Okay, so let's do that. Again, we asked two questions. Is this function even or odd? Is k bigger than 0 or k less than 0? Now for this one, let's look at these two parts. As it turns out, if you simplify this function, you take negative 2. Remember, when you multiply these, you add the powers from chapter 2. So we take 2 plus 3, and we get x to the 5th. So we look at this function and ask, is it even or odd? Well, we got a 5. That makes it even. That makes it odd. Dumb. Okay. One of those days. All right. We got a negative 2. That means it's less than 0. So from this information, we can actually go to our grid up here and answer the question. It's odd. It's less than 0. That tells me it's going to have this end behavior, which tells me we have x goes to negative infinity, f of x goes to infinity, x goes to infinity, f of x goes to negative infinity. Or the shorthand version is left up, right down. This first one's the answer that I want you to be able to give. This second one, though, is a great way to think about it because, again, it makes the picture make sense. We're in this category. What's happening? The left side is going up. What else is happening? The right-hand side is going down. This information tells that same story, but it's a little tougher to read. And so I want you to be able to do this first one, but know how to interpret it as well, because if you can't interpret it, then you don't really know what you're doing. So make sure you can do both. And so if the question asks for what's the end behavior, that's all you got to do. Is figure out which these boxes it's supposed to fit in, and then write down the answer in blue. Okay, next. So we've done all the main work that has to do with a power function. This is it. And that's about a quarter of your homework assignment. So now let's talk about the second part, which has to do with polynomials. Boom. Okay, let's start with the definition. Okay, the definition in the textbook is, it's interesting. So I'm going to show some examples and kind of explain what makes a polynomial versus a yes or no category. So the definition of a polynomial is any function that fits the following form. You have a sub n x sub n plus a n minus 1 x n minus 1 a1 x1 plus a0. So this looks all fancy, but let me just show some examples of what is versus what is not. So what is? X squared is a polynomial, but so is x squared plus 1. So is x squared minus x. So is negative 3x cubed plus 4. All four of these are polynomials. How do I know that? They're just a collection of constants being applied to powers and then being either added or subtracted. So this always represents a polynomial. But if you ever see any radicals or not, absolute values are not. If you randomly see a trig function, sorry, it's not a polynomial. Okay? And this can be in any form. You could be added, you could be subtracted, you could be multiplied, you could be divided, but if it's a radical, it's probably not a polynomial. Same with an absolute value, same with a trig function. It's just not a polynomial. Now, when it comes to a polynomial, there's two major things you want to remember. And these two things are the degree versus the term. The degree is the highest combined power. The term is the number of pieces. So if we look at these examples, let's go ahead and break these examples out. We have x squared. We have x squared plus 1. We have x squared minus x. We have negative 3x to the third plus 4. And I'm going to put a couple more here. Let's go with 6x cubed minus x to the fourth. And let's go with a long one here. 3x cubed minus 4x squared plus x minus 1. So let's talk about each of these degrees and term. So this first one, the degree would be a 2. How do we know that? What's the highest power? For the second one, the degree would also be a 2. For the third one, 2. It's the highest power. For the fourth one, that's actually 3. Again, highest power every time dictates the degree. For this one, the highest power is actually a 4, so it would have degree 4. And down here, highest power is a 3, so degree 3. You can only ask these questions if it's already a polynomial. So remember, if it's a polynomial, we can ask about the degree, we can ask about the term. But if it's not a polynomial, we don't even bother asking these questions. Because it's kind of like asking what brand of car is a tank. Like, it's not a car, so asking that question doesn't really have any meaning. Terms is how many of them. So in this case, this first one, there is one thing being added or subtracted. There's one term. This one, there are two things. So there are two terms. This one, two things, two terms, two things, two terms, two things, two terms, 1, 2, 3, 4 things, 4 terms. Notice that the number on those terms doesn't matter. Hey, it's a negative 3? Cool. There are 2 of them. There's a negative 3x to the third, and there's also a plus 4. There are 2 things, 2 terms. The power also doesn't matter what these coefficients are. Hey, negative 3? Cool. It's still a 3, because it's the power that matters here. The 3 is the power, so the 3 is the degree. The highest number here is a 4, so the 4 is a power, so the 4 is the degree. It doesn't matter what the number out front is when it comes to the degree. So there we have it. This is how you identify what type of polynomial you're dealing with. So in this case, you always want to note 2 factors about this. And the last one is called the leading coefficient. The leading coefficient, or as I'll refer to it as, is the LC. It is the number in front of that highest power. So for this one, my leading coefficient is actually a 1, because in this example, the 1 is how many x squareds we have. In the same example, 1 is the leading coefficient, because it's how many x squareds we have. Notice, it's only the piece with the degree that we ask for the leading coefficient. So for this example, it's also a 1. Because again, the x squared is the one determining the degree, and the number in front of that x squared is a 1. For this one, my leading coefficient is actually negative 3. This is the only time you can have negative numbers, is when we talk about leading coefficients. So, how do I know it's negative 3? Well, x cubed determines the degree, and its number is negative 3. For this one, a little bit tougher. What's determining the degree is the 4. So the number in front of the 4 is actually a negative 1. Because how many x to the fourth are there? Negative 1 of them. This one, the number that's determining the degree is the x to the third, and its leading number is 3. And so when you're writing these out, you can see that you always have like a x to the n power plus a bunch of other stuff. You'll always have it in this form, which is exactly what that definition up here states. This a is what we call the leading coefficient. The n is what we call the degree. And the number of terms is just the terms. So if there's 5 things being added or subtracted, then the term is 5. It's important to note all of these pieces exist for any one particular polynomial. And so when you ask these kinds of questions, you have to look at it in those forms. Like, you have to ask the question, what is the degree? What is the degree? How do I know it's the degree? What is the number of terms? What is the leading coefficient? And see them in those terms. Sometimes pieces can match. Like for this problem, the degree is 2 and the number of terms is 2, but the leading coefficient is different. And sometimes they can all 3 be different. Like look at this one. The degree is a 4 because it's the biggest number in the x power. The number of terms is 2 because there's 2 things, 6x to the third and negative x to the fourth. And the leading coefficient is negative 1 because the biggest power is the negative 1. The 4 is the biggest power, so the negative 1 is the one that matters. So these are all talking about the degree, term, and leading coefficient, which is a big part of your homework. And it leads into the next piece of your homework, which is actually something we just saw. End behavior. Now, when it comes to a polynomial, anytime you talk about polynomial, the nice thing is you can reuse the information from a power function. But you have to be specific and pointed when you do this. What you're going to do is your k is your leading coefficient. And your number, your power, is just the degree. So again, let's look back at all these examples. I can predict the end behavior of all of these with just the information we have. So let's take a look. We have a degree of 2 and a leading coefficient of 1. So I have a degree of 2 that makes this even with a k bigger than 1. According to my notes, if my k is bigger than 1, it's bigger than 0, and I have an even function, well, that would tell me that it's going to be in this first category. So I can write down the end behavior for that function. But notice I only use the degree and the leading coefficient to answer that question. So for this one, same thing. It has a degree of 2. It has a leading coefficient of 1. So that tells me that it's going to fit in this first category, and therefore have up end behavior, or negative infinity to infinity and infinity to infinity. If, on the other hand, I go down to like one like this one, it has a degree of 3 and a leading coefficient of negative 3. The degree of 3 tells me it's an odd, and the leading coefficient of negative 3 tells me it's the bottom row. So it would have this end behavior. And in fact, if you were to graph this function, it would look kind of similar to this. Not exactly the same, of course, but as we go to the left, it would go up. As we go to the right, it would go down. And if we just continue down this list, it keeps happening. The power of the degree dictates the end behavior every time. So for each one of these, you can go through and be like even, k bigger than 0, and then write down your piece. You could write, so even, k bigger than 0. So all 3 of these first equations are going to look very similar in terms of their end behavior, because again, they're even functions, and the k is bigger than 0. This fourth one is odd, and the k is less than 0, so it's going to look a little different. It's going to fit the category of this odd less than 0 branch. And the next one has a 4 and a negative 1. So this is even because it's a 4, but k is less than 0 because it's negative 1. That tells me it's going to fit into this category, meaning it's down, down, or negative infinity, positive infinity, negative infinity. And so you can answer all these pieces just by knowing the degree and the leading coefficient. The number of terms is just helpful for another piece we're going to talk about later, but really it's these first and last ones that matter the most. So for this one, I can see that the leading coefficient is the 3, which we know is bigger than 0, so it's going to be in this top row. And we know that the power on it is a 3, because it's the biggest power we have. And it's the biggest power we have, that makes it odd. So it's going to have this end behavior, which is a pretty powerful tool for having so very little information to talk about. Like, I don't need to graph this to predict what's going to happen. I can just look at this picture and say, I know it's going to look roughly like all other evens with k bigger than 0. It's going to look like this. Just looking at this function, I can tell from the two pieces I know, it's an even power, because the degree is even, and the coefficient's positive, so it's going to look like this. Whereas here, I know it's an even power, but the coefficient's negative, so I know it's going to look like this one. And so I can answer all these really complex questions by just being able to identify very simplistic pieces. And this is the advantage of having these kind of leading coefficients and understanding how the behavior may work. Now, before we go any farther, it's important to note that you may need to simplify some stuff before you can answer these questions. And it helps to write it in the correct order. So, when determining end behavior, one big step I would recommend every single time is always to simplify if you can. What do I mean by simplify? I mean, combine like terms if they can be combined. Like, if they can be added, add them. If they can be subtracted, subtract them. Like, just do it. Other things you might be able to do. You might have to FOIL. If there's something being squared, you may have to FOIL it out. And you may have to distribute if there's a parentheses. Like, you need to be able to do these 3 steps. Because you cannot tell me the degree unless it's simplified. You cannot tell me the leading coefficient unless it's simplified. And so for many examples, the biggest difficulty is going to be what form is it in right now, so I can actually answer that piece. And to illustrate this really well, I'm actually going to go to an example from the text and from the homework, so you can kind of see how this fits together. So it says determine the end behavior. Notice for number, what's a good one here? Number 24. So it says 2 minus x to the 7th power. Now, if I were to determine the end behavior, I need to know 2 things. I need to go to the leading coefficient. I need to know the degree. I need to be able to answer both these pieces. Now, I don't want to do this FOILed out. But notice, I don't really care what the leading coefficient is. I care, is it positive or is it going to be negative? That's really what I care about. And then for the degree, I just care about what the number is going to be. I don't care if it's fully simplified as long as I know the number. So in this example, one of the things you can do is some tricks. Example, if I FOIL this out, eventually I'm going to have to do this term to the 7th power, which tells me right away my degree is going to be a 7. Yeah, there's going to be a bunch of other stuff involved, but the degree is going to be a 7. What then counts is what's the leading coefficient going to be, and is it going to be positive or is it going to be negative? Notice I don't care if it's positive 5, I care if it's positive. I don't care if it's negative 3, I care if it's negative. I don't care which value it is, I care if it's positive or negative. In this case, it's negative. Because remember, negative raised to the 7th power is going to be a negative number, because you're taking a negative times 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 a negative. You're going to get double positive, double positive, double positive, and you end up with 1 extra negative. So that 7th power is going to mean that this thing is going to be negative. Now, because it has k less than 0, and because the degree is odd, I can answer the question of what the end behavior is going to be by just looking at my list and seeing, is it even or odd? Well, it's odd. Is k bigger than 0, less than 0? It's less than 0, so it's going to have this end behavior. And that's all I need. I don't need to know the exact equation, because the question didn't ask for the exact equation. It said, what's the end behavior? And so that's it. For this function, the answer would be, just copy it down, x goes to negative infinity, f of x goes to positive infinity, and x goes to positive infinity, f of x goes to negative infinity. Or the shorthand, up, down. So, always put it in the order left, right. So, that's how you do it. You have to first figure out what the degree is, and then figure out what the leading coefficient is. Note that for this problem, and for many of the problems like it, if I go back to text, many of them are already pre-simplified for you, which is real nice. They've been very helpful to you. Okay? But the question is usually going to be, if I need to simplify it, what are those steps? Like on 23. 23 is an assigned problem. You're going to have to distribute that x squared. And then once you got to distribute, you're going to have to yourself ask, what's the biggest power? Okay? All right. Next. So we're more than halfway done now. Next part is to ask questions about things like intercepts. And all these are going to be looped under a big category called local behavior. Now, what's local behavior? Local usually means what's happening in the middle. So end behavior tells you what's happening all the way to the left and what's happening all the way to the right. Local behavior is what's happening kind of in the middle. It's where the most unique things can happen. If you look at any function, the middle part of it is always going to be the most interesting. It's going to have the most stuff going on. It's where the most intercepts are going to be. It's where you can have the most what are called turning points, which we'll talk about. Like, there's a lot of pieces in here that we need to discuss. And so let's discuss them. First big category, intercepts. Now, in the intercept category, there are two big ones we've talked about so far, and they're still here. You have y-intercepts and x-intercepts. Now, to determine the y-intercept, if the question asks about intercepts, that's one of the things you got to be able to find. To determine the y-intercept, all you have to do is plug in x equals 0 and solve. So in other words, everywhere there's an x, just make 0 and then simplify as much as you can. X-intercepts are always the more fun one. They always have more work involved. They always have more things that they can do. This is because, while in general, for most of these problems, you're only ever going to get one answer when it comes to the y-intercept. But when it comes to the x-intercepts, these can often have many answers. And so there's a lot of different ways you can find the intercepts. The first and biggest way is by looking at the graph. Just look at the graph and see, is there an intercept on the x-axis? So look at the x-axis and ask yourself, where are we crossing? What values do we get? And if you have a graph, of course, you can always do that with the y-intercept too. Just look at the y-axis. If that doesn't work, though, you can always plug in x equals 0. So this is the best way, and it involves having a graph. And notice for some problems, like if you scroll down a little bit, it's going to ask things like determine the turning points and numbers of the function. That kind of information, like if I ask the question, how many intercepts does 35 have? Well, we can look at this graph and be like, there's an intercept here and an intercept there. There's only 2 of them, and I can tell exactly where they are and what kinds they are. So all that information is much easier to read from a graph. The harder ones are when we don't have the graph. So if you don't like graphing, that really inhibits on what you can do because, well, graphs are easier. If you can learn to graph, then graphing makes everything else easier. But if not, there's always options. So let's talk about some of the most common options you can have. You can, depending on the situation, you want to look for factors. This is usually used when you have, multiple parentheses. If you have multiple parentheses, what you're going to do is set each one equal to 0 and solve. We'll go through an example of that in a second, but this is the big detail. So if I look at something like, 26, perfect example. Okay, 26 says find the intercepts of the function. And what we have -2 times 3n minus 1 times 2n plus 1. And it wants to know what the intercepts are. Well, if I want to find the x-intercepts, what I can do is I can just take each of these pieces and treat them as three separate problems. I set -2 equals 0. I set 3n minus 1 equals 0. And I set 2n plus 1 equals 0. And then I solve. This first one doesn't solve because -2 never equals 0. This second one gets me 1/3. I add the 1 over and divide. The second one gives me -1/2. I add the 1 over, or subtract the 1 over and divide by 2. These are my x-intercepts. And that's how we find them, as we look at factors. So that's a perfect example. The question says find the factors. These are the x-intercepts. If I wanted to find the y-intercepts, so this is x-intercepts. If I want to find the y-intercepts, I do a slightly different approach. I take this function, -2, and everywhere there is an x, or in this case an n, right? I just replace it with 0. And solve. 3 times 0 is 0, minus 1 is -1, so we have -2, -1. 0 times 2 is 0, plus 1 is 1. So I have -2 times -1 times 1. Negative times a negative makes it positive. 2 times 1 is 2, times 1 is another 2. So this would be the y-intercept. So in this case, I have 2 x-intercepts and 1 y-intercept. And I find them by radically different methods. Okay? But notice that they all fit into this, can I factor it form. Another common thing that might happen, so this is your example of one where it involves, factoring it, is some specific ones are quadratics. Like quadratics, you can obviously use the quadratic equation. That was that negative b plus or minus the square root of b squared minus 4ac all over 2a. That one. And that can also find it if it's a quadratic. So if I look at something like, there we go, number 30. Number 30 combines together the second and third examples. Like it's got factors, but one of those factors is a quadratic. And so when I do number 30, I can do it by taking the two pieces. If I want to find the x-intercept, I take those two pieces, the x plus 3 and the 4x squared minus 1, and I just split them apart. I do x plus 3 equals 0, and I do 4x squared minus 1 equals 0. And then for these ones, I can either solve them if I choose, or because this one's a quadratic, I could use the quadratic equation. So in this case, I get x equals -3. If I do the quadratic equation, I get 1/2 and -1/2. And those are my x-intercepts. And I'm just shorthanding a lot of stuff to get to the example. But it's an option. Like, if I can't factor it, I can use a quadratic. But notice that for each of these examples, that's always a possibility. So, there we have it. Besides intercepts, there's one more thing we can talk about. And these ones are called turning points. A turning point is a place in the graph with a shift from increasing to decreasing. It's easier to explain a turning point with a picture, so let's look at the book. Okay, here we go. Perfect example. This showcases the three things we already talked about. The x-intercept and the y-intercepts. We have 3 x-intercepts in this example. -1, 2, and 4. So 1, 2, 3 times across the x-axis. And 1 time across the y-axis. And this example is actually really great if you're ever stuck on how to do these problems. So example 8 is a great one to look at. Same with the factoring piece down here. It's very good. Okay, but what's a turning point? Well, in this case, a turning point would be one like this spot right here. I'm going to zoom in a little bit. Up here, see how it's going up, going up, going up, going up, going up, until we get to right here? This dot, this very topmost point, is called a turning point. It's a place where the function turns from going upwards to going downwards. Or, alternatively, this point down here is also a turning point. It's where the function was going down, but now suddenly, whoop, it's going up. I like to think of these as, if I'm driving, this is the fun part. Like, I hit the top of the hill, if I'm going fast. Hit the top of the hill, that's where your stomach starts to rise, and you sort of feel like you're flying a little. Hit the bottom of the hill, that's where the bottom of your stomach hits, right? The tops and the bottoms, these are turning points. Now, to be a turning point, it has to have a change happen. So if you look at this example, zoom in a little farther even, there's a turning point right here because it's going down and then it starts creeping back up a little. So this is also a turning point. Yeah, it's not creeping up as much, but it did change. It was going down and now it's going up a little. Here is a turning point because it was going up a little, now it's going down a little. It doesn't say how much to increase or decrease. It doesn't specify it has to be going at least this fast to stay in the zone. No, no, no. A turning point is any place where this happens. And so this graph actually has 3 turning points. One here, and one there. Decreasing, 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 stops. Increasing, 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 stops. Decreasing, 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 stops. Increasing, increasing, increasing. So you can see that there are 3 turning points. Yes, they're close together. Yes, it's only a little turn. But a turn's still a turn. If you've ever taken a driver's test, the only points I missed on my driver's test was because I didn't put on a turn signal when I should have. And it was in a situation where I was like, it doesn't feel like a turn because it wasn't turning very much. It was at that the place in Anderson, if you've ever been out by the stoplight. If you go there and you're supposed to have a turn signal on if you're making that turn, even though it doesn't feel like it because you're not really making much of a turn. Like, you're supposed to still have a signal on. Or if you go out Old 76 going towards like Cassville, you know, there's that one spot in the road where it creeps off to the right and you end up joining with another road. Well, you've technically turned. You're supposed to have a turn signal there. It's a turning point. It may not be much of a turn, but it's a turn. So, in this case, this is a definition of a turning point. A turning point is simply a place where the graph has a fundamental shift from increasing to decreasing or decreasing to increasing. And so let's look at some more examples. So in this picture, zoom in. This has 1 turning point, 2 turning points, 3 turning points. Turning point, turning point, turning point. This one down here has 2 turning points, 1 turning point here and 1 turning point there. It's a place where the function has shifted from going down to going up and from going up to going down. That's what makes it a turning point. And if I look at some of these examples here in the text, in the homework, 2 turning points, 1 turning point, 1, 2, 3, 4 turning points, no turning points, 2 turning points, 3 turning points. You can very easily visually see the number of turning points. And there's actually another way. So if you have a graph, you can just count. Just count them out. How many are there? 1, 2, easy. If, however, you don't have a graph, you can actually predict using the degree. So how do we do that? Well, there's actually a little property in the text, and I'm going to go to that right now. And this will be our last major part of the notes is these 2 pieces. Okay, here we go. This little blue box is the last thing I would have you guys write down for your notes, and I'm going to put them with the 2 pieces. So for intercepts, so this is always the case. If you're asked a question about intercepts, the maximum number of x-intercepts is equal to the degree. And so you can make predictions about what the degree is by using the number of intercepts, and you can make predictions about the number of intercepts by using the degree. So for example, if I look at a function, and let's look at this one right here in the text. Example. Okay, it has a degree of 10. That tells me that it has at most 10 x-intercepts. These 7, 4, and 3 do not matter because they're not the biggest power. The biggest power dictates the degree, and the degree dictates the intercepts. This does not mean there are 10 intercepts. It means it's the maximum number. The max is 10. Okay? Notice how it says that. So there are at most 10 intercepts. And notice there's a secondary part of this too. If you subtract 1 from the degree, it tells you the max number of turning points. So, in this example, it says we have x to the 10th power as the degree. That tells me there is at most 10 x-intercepts and at most 9 turning points. If you look here, 12. Notice how I disregard the 108, there's no x. I disregard the 9 because 12 is bigger. Same with the 4 and the 3. So the 12 is what's happening. This tells me that there are at most 12 x-intercepts and at most 11 turning points. And you can even work backwards. There's a great example of this here. How many x-intercepts are there? 2. But how many turning points are there? 3. If there are 2 x-intercepts, that means it could be degree 2. Because remember, the degree could equal the max number of intercepts. But both these can be true at the same time. And they could be different numbers. And so if the question asks what's the least or the greatest, you need to pick from these two about which one's the better one. So if you look here, if I look at this example, there are 3 turning points, which tells me that is equal to the degree minus 1, which tells me this could be a 4th degree function, which is exactly what it says right here. In this example, there are 2 x-intercepts, suggesting it could be a degree of 2 or more. However, there are 3 turning points, suggesting it could be a degree of 4 or more. It'd be reasonable to say it has to be at least 4. The reason being is, if it's 2, then it can't possibly have 3 turning points. Because remember, if it's 2, then it would break this rule. Because if the degree was 2, 2 minus 1 is 1, the maximum of turning points is 1, but it isn't 1, it's 3. And so you can use this information to work backwards, which is the last piece of the homework assignment. It's a logic puzzle to making sure does it make sense. And you can do this for any function. Look here. I can predict what a degree of this should be by looking at 2 factors, the turning points and the x-intercepts. This one, there are 3 x-intercepts, -3, -1, and 2, which tells me the degree could be a 3. But there are 2 turning points. 2 turning points means if I subtract 1, I should get 2, so that means the degree could also be 3. So for both these, it's indicating that this should have a degree of at least 3. This is a degree 3. And notice how I know it's a degree 3, or at least an odd degree, because it follows my end behavior. Like, it makes sense. It has this end behavior, so I know it should be an odd number. So 3 makes sense. 5 doesn't make sense, though, because it doesn't really match with what I'm given, right? We don't have 5 x-intercepts, and we don't have 4 turning points, so 3 is a reasonable guess because it's odd, therefore it matches the end behavior, and it matches the rules we have based upon the number of turning points and number of intercepts. You can do this with any graph. That's a polynomial graph. So let's look here. It has 1, 2, 3 x-intercepts, 2 turning points. It follows this behavior. This tells me, the behavior tells me it's going to be odd. 3 x-intercept tells me 3 is a good answer. So it makes sense. Over here, for 32, I have 2 x-intercepts, and I have this behavior, so I can look at this list and be like, oh, it looks like this one. This tells me it's going to be even. So that tells me it's going to be 2, it's going to be 4, it's going to be 6, it's going to be 8, it's going to be 2, it's going to be some even number. But which one? Well, I have 2 x-intercepts, 1, 2, and the x-intercepts tells me the degree that it could be. 2 makes logical sense. Number 33, same process. We have 1, 2, 3, 4 turning points. We have 1, 2, 3, 4, 5 intercepts. If we have 5 intercepts, that means the degree could be 5, and that matches the behavior, right? It looks like this one, where the left-hand side is going upwards, the right-hand side is going downwards. Notice, as I said before, the middle piece can be very different. The question is what's happening as we go to the left, what's happening as we go to the right. This middle piece can be all over the place like it is on number 33. That's it. That's your entire homework assignment. Questions about a lot of end behavior stuff. Notice again, as we've been discussing before, a lot of these assignments are not dealing with, a lot of hard math. It's just, do you understand the concept that's going to be getting tricky? And so, again, our homework assignment for tonight, page 372/390, 1 through 45 odds. For many of these problems, note the difference, whether they're power function problems or polynomial problems, because they are slightly different, even if they do use very similar rules. So make note of that. And I'll be posting 5.3 tomorrow as our last section of the week. I hope to have the test graded by tomorrow as well, so we can get all that information in, and I'll do it for today. I hope you guys have a good rest of the day, and good luck in your homework. If you have any questions, make sure to message me about them. I will try to answer those on Saturday, and I will see you guys next time.